Okay. First, let me begin with a couple of announcements. Next Monday is a holiday, and so we will be meeting on Tuesday. Tuesday follows a Monday schedule. So we have two consecutive classes, Tuesdays and Wednesday. And in the interest of students enjoying the weekend, I'm not going to have the quiz on the Tuesday class. We'll have the quiz on a Wednesday. And the homework that I will post will be due either Wednesday or Thursday. So there'll be some gap in students can get some work done and also enjoy over the weekend. All right, let's get to our MOSFETs. Do a few example analyses, and then we'll get to logic gates. Oh, wrong. Okay, first up is a graphical method of determining the Q point values for a MOSFET, right? So we have a straightforward simple circuit of a MOSFET biased with one single drain resistance. Applied VDD is 10 volts, and applied VGG on the input side is 2.4 volts. We are not given any other information except provided with this output characteristic, a plot of ID versus VDS. And we are asked to determine the Q point values for both ID and VDS. Okay, so because it's the Q point values, there's a subscript of ID, subscript of Q applied to both. So we have IDQ and VDSQ. All right, so this is essentially the same as the load line analysis we've been doing for the diodes, the Zener diodes, the BJTs. Same straightforward approach, sorry. And in the case of MOSFETs, it's easier because the gate is actually isolated from the device. Because the gate is isolated, there is no current that actually flows into. And so on the input side in a BJT, we'd have the base current IB. In a MOSFET, we do not have to worry about that. So we simply apply KVL on the output side. When you apply KVL on the output side, we have three voltages. We have VDD, we have the voltage drop across RD, and VDS. Right? We have current ID flowing through the device. So we can write the KVL as VDD minus VDS minus IDRD equals 0. Plug in all the known values, meaning RD and VDD, and we obtain VDS minus ID times 100 is equal to 10. And we obtain two unknowns in our equation. Okay, two unknowns in the equation. Now, so this is the equation describing a line, which is the load line. To determine the plot points for the load line, we simply take the X and Y intercept values. So right here and right here. So we plug in VDS equals 0, obtain ID. Then we plug in ID equals 0 and obtain VDS. Those 2 points correspond to these points, or sorry, those two values correspond to these 2 points on the graph. And once we have them, we join to obtain our load line. And once we have a load line, it intersects all of these points in a single spot. Now we look at VGG. VGG is 2.4 volts. So we look at the plot for 2.4, which is right here. Now, these are different values of VGS. Again, in a BJT, we had different values for IB, the base current. Here it's VGS. Depending on how low or high VGS is, the channel is correspondingly smaller or larger. Since there is no source resistance, VGS is going to be equal to VGG, because supplies for both connected to ground at the bottom. So VGS is equal to VGG. And so we can look up that Q point right here. And the extension or the coordinates of the Q point give us the values of IDQ and VDSQ. We can write IDQ is 52 milliamps and VDSQ is 4.75 volts. And that's it. Yes, absolutely, it does. Slope of the line would be, actually the inverse slope of the line would describe the resistance, RD. So the question being asked was about the slope of the line, and the answer is yes, absolutely. It's minus 1 over RD. Inverse of the resistance. Okay. All right. Now let's look at another example, but this time no graph. Okay, no graph. Let's say this is not available to us as an engineer, right? So then how could we determine the Q point values? Well, this time we are given threshold voltage VTN of 1.4 volts and a K parameter value of 48.5 milliamps per volt square. Okay. All right. Requirements remain the same. We are trying to determine the Q point values for ID and VDS. Okay, first things first. This time we are given the threshold voltage. So we need to look at values for VGS that are being applied at the gate and the threshold voltage. Larger or lower? VGS is larger. So if it's larger, that means the device is not cut off. It is on. And when it's on, we have two more options. Is the device in the active saturation region, or is it in the linear triode region? So we have to make an assumption. Now, typically similar to the BJTs in the active region using as an amplifier, we will choose is the saturation active region and not simply in the linear triode region. Okay, so once we have that, we know that we have two unknowns. We need to find VDS, we need to find ID. Well, standard equations for ID exist, and so that's what we're going to use. If we assume saturation region, ID in the saturation region is given by K times VGS minus VTH squared. Plug in the values, and we calculate ID. It's 48.5 milliamps. Okay, 48.5 milliamps. To obtain one of those values, now to obtain the other one, apply KVL at the output. On the output side, we have three voltages: supply voltage VDD, drain source voltage VDS, and the IDRD voltage drop. We plug in the values. Again, VDD is 10, ID we just obtained. So we obtain VDS as 5.15. So we obtain ID and VD values. Now, once we obtain those values, the next question is our assumption valid? Right? We calculated based off the assumption that the MOSFET is in saturation active region, and hence we use the equation, or we use this equation. So we need to verify whether it's in saturation. So we check for the assumption by calculating VGD. VGD is VGS minus VDS, gives us minus 2.75, which is less than the threshold voltage. If it's larger than the threshold voltage, then the channel is not yet pinched off. Because it's less than the threshold voltage, VGD, the depletion region at the drain end is larger, the channel is pinched off. Okay. So VGD is less than the threshold voltage, hence the device is in saturation. And it's verified. All right, any questions from anyone? All good? Okay. Let's look at a slightly more complicated problem. So these next two problems are a self-bias or the voltage divider bias circuit, also known as the 4-resistor bias circuit. A 4-resistor bias. We have two resistors attached to the gate and an RD and RS resistor on the output side. Threshold voltage is given as 4 volts. K parameter is given 0.2188. We are asked to find VGS and ID at the Q point, but we are also provided with VDSQ as 8 volts. Now, this is a solved problem, and because it's a solved problem, there are several parameters that are given to us. As working engineers in real life, you might come across a system where everything is unknown. So we have to pick, right? We have to pick values for certain quantities. So in this case, let's say that the question being asked is, we have a MOSFET and we want to bias it at the operating point of 8 volts. So determine what value of VGS would be required to do so, right? We always, as design engineers, we always work backwards. We have our system, we have our application, we have our purpose, and then we need to design the system to fit that purpose. And so we need to determine VGSQ. Okay. So first things first, we have the voltage divider network here. Applying VDD to it. This goes into the FET. This becomes VGG. For convenience sake, both R1 and R2 have the exact same value, which is 1.2 mega ohms. Okay. And so the voltage is divided in exactly half. VGG is VDD times R2 over R1 plus R2, cut in half. The gate resistance is R1 parallel R2, again cut in half. 1.2 mega ohms in parallel with 1.2 mega ohms gives us 600 kilo ohms. All right. So far, so good. Okay. Yes. Uh-huh. Yes. So question me asked is about this one, right? Yes. This one is technically actually connected to the source right here. And that's the body, the fourth terminal. Okay. Let's see. All right, so now we can begin. We apply KVL on the input and the output side. Everything is an unknown right now, right? We only have VDS, we don't have VGS, we don't have ID. So we have our standard equations, right? We have the ID values, ID equations in the saturation region and the triode region. So we have those equations. But all of those equations also require VGS, right? So we can't directly find ID. Also, if you apply KVL on the input side, this time VGG is not the same, VGS is not the same as VGG because we have a source resistance right there. And so VGS would be VGG minus IDRS, or the voltage drop across RS. And so we cannot take even that path, right? And so what we need to do is we need to use other methods. Okay, one method always available to us is applying KVL. So we apply KVL on the input side, we apply KVL on the output side, and then we manipulate the equations to obtain it in the form that we require. All right, so if you apply KVL at the input side, we obtain VGG minus VGG plus IGRG plus VGS plus IDRS. So it's 1, 2, 3, and 4 voltages. Okay, so we have 4 voltages. But here's what makes it easy, right? No input gate current. If there's no input gate current, this quantity is already gone. This is 0. And so we have 1 voltage drop gone. Only thing remains is VGS and IDRS. VGG we calculated to be 15, so we plug that in. And later on, we need to find IDQ, so we're going to express this entire equation in terms of IDRS. So IDRS is 15 minus VGS. We don't know this beforehand, obviously, but again, this is a solved problem, so we know that we need, and so we manipulate it in that format. KVL at the output gives us 4 voltages again, VDD minus IDRD. So minus IDRD minus VDS and minus ID times RS. So unlike a BJT where IE and IC are approximately equal, here ID and IS are exactly the same. No difference, it's the same channel. So IDRD and IDRS. Now what we can do is we want to obtain an expression or equation for IDQ. So we can take this and plug it into here. And when we do that, we obtain this. Okay. You obtain this. All right. We want to solve for ID and VGS. Right now we don't have VGS, but you can find VGS later on. So we rearrange all the terms to obtain it in the form for IDQ. So once we obtain it for IDQ, then we plug in all the known values, which are VDD and VGG. This technically is simply the voltage drop across the drain resistance RD. It's ID times RD is equal to 15 minus VDS plus VGS. That's all that's actually been done, right? So we obtain an expression for IDQ. Now here's the main point. We have an equation that relates both ID and VGS. So we're going to plug the previous equation or equate it in here. And once we do that, we're going to obtain a quadratic. It's a square, so we all know where it's going. It's going to give us a quadratic equation, which is listed here. Everything that's there in the coefficients, sorry, not coefficients here, the constants, VTN, KRD, KRD, and VT. All of those values are known to us. So we plug all of those values in, calculate those coefficients, and we obtain minus 8.45 and plus 12.8. Then we simply solve that quadratic equation. Once we solve it, we obtain two answers, two roots. Which of these roots, which of these values is correct other than being marked? Well, for that, we have to go at the top and we have to look at this. Our assumption was that the transistor is on and it's in saturation mode. Well, for the transistor to be on, VGS must be larger than the threshold voltage of 4 volts. Conveniently, the values are such that one of them is less. Obviously, that's never going to happen in real life. As an engineer, it would be up to us to design it. So either both, if you are designing this from scratch, for example, going on a little bit of a tangent, as a real life engineer, if you're trying to design something like this, VGS might be below 4 volts. Device would never be on, so we'd have to go back to the beginning, change a few things, and redo the calculation. Or both of these values could be above the threshold voltage. Then we wouldn't know which one to pick. And again, we would have to plug in those values and determine what would actually work. Conveniently, I mean, not conveniently, convenient for us, the values are such that one of these values is below 4 volts. Obviously, that would not work. So we choose 6.48. We plug it into the above equations. And once we do that, we obtain value for IDQ. And once we obtain value for IDQ, again, we plug it into that KVL expression, and we can obtain value for RS. And that's how we would end up designing or working a biasing circuit. All right, any questions? Yes. Question being asked is, what does these having two values mean? It's nothing. It's just a mathematical calculation. Only one of them is correct. Well, let me put it this way. In real life, there might be two values. So one of the values could be like 6.48, and the other root could be, I don't know, like 5, maybe, could be 9, let's say. So in that case, both values or both roots are above the threshold voltage. So then we have to take that, determine the value for ID and RS, see which one makes the most sense to fit our system, right? Threshold voltage is 4 volts. Anything we apply in excess is gate overdrive. So gate overdrive voltage could be 1 volt, 2 volts, 3 volts. System will still work. So system would work for 6.48 volts. If this 1.97 was 9 volts or like 5 volts, it could possibly still work. So it just depends on what values work best for our application. If this happened in, let's say, if I design a problem beforehand, I wouldn't know the answer. So let's say in the final exam or on the quiz, students might end up with 2 values. Well, yeah, we ended up with 2 values. It doesn't mean anything. Both of those could work just fine. And then depending on our application, we might constrain it to like, one of them. In this case, it's rather straightforward. One of them is below the threshold voltage, so it makes our job easier. Does that answer your question? Okay. All right, so the next one is exactly the same. It's directly from the book. So I'm going to assign it for student practice. And what I want students to do is open up the book, look at the given parameters, solve through it without looking at the solution. And then because the solution is already there, you can automatically verify your answers. And so go ahead and do that. And once you're done with that, if you have any questions along the way, let me know. I'll be available over the weekend. Okay, from here on, let's turn our attention to logic gates. CMOS technology. CMOS, as a brief reminder, is basically the usage of both N-channel MOS and P-channel MOS together in circuits to form what is known as complementary MOS structures, hence CMOS. And you're going to see how we can create logic gates using NMOS and PMOS transistors. So first up is the logic inverter, A not Z. Z is actually A bar. Output is always opposite of the input. If input is logic 1, output is logic 0. If input is logic 0, output is logic 1. In terms of circuits and voltages, 1 would be plus 5 volts and 0 would be 0 volts. So a logic inverter or a NOT gate can be implemented with a single NMOS transistor connected to VDD via a resistor, which is shown here. Okay, so A is the input that is going into the gate of the MOSFET. A is going as input to the gate of the MOSFET. It is also input to the inverter gate. You have A and you have Z. Operation is rather straightforward. If gate voltage is 0, then the MOSFET is off, below threshold, so MOSFET is off. If MOSFET is off, then output is directly connected to VDD. So you apply 0 at the input, and you get VDD at the output. Hence, inverted. Make sense, right? Now you apply logic high at the gate, or plus 5 volts at the gate. Presumably, the plus 5 volts is larger than the threshold voltage. So the gate turns on, the gate turns, not gate. The MOSFET turns on. If the MOSFET turns on, it directly connects the output to ground. That small resistance that we see here is basically the drain resistance, or sorry, the channel resistance. Because current is flowing through a channel, and that current is not infinite, that means that the channel has some resistance. And that is modeled by this resistance right here. That's the channel resistance. Nevertheless, even with that small resistance, it provides a direct pathway for it to connect to ground. So the output is very close to 0 volts. So apply plus 5 volts at the gate of the MOSFET, meaning logic high as input. Transistor turns on, connects the output to ground, output is 0. Hence an inverter gate. And we saw this with the end of the BJT chapter, where we took a single BJT and we could use it as a switch and create an inverter gate. All right, next up is logic OR and logic NOR. OR gate is A plus B. Logical OR is mathematical sum or addition, right? Mathematical addition. So in this case, we require two MOSFETs. We connect them in sort of parallel. The gates are not connected. The drain and the source are connected together. Hence, we consider them to be in parallel. But as a quick reminder, OR gate A, B, and Z, 0, 1, 1, 1, 0, 1, 1, 1 is 1. An OR gate, the output goes high if even a single input is high. Okay, if even a single input is high. And if you look at the configuration of the transistor, we can see why. Now, what do we see? Let's look at the explanation. We got two transistors, right? Let's just take the first transistor, A, right? Let's say A is 0. If A is 0, transistor is off, then your output is plus 5 volts. So if either one is 0, output is going to plus 5 volts. So now you add in a second transistor, which is B. If B is also 0, both of the transistors are off, output is connected to plus 5 volts. Hence, we should obtain, what do we obtain? If you apply 0, 0, and output is connected to plus 5 volts, we obtain 1, right? How about if it's 0 and 1? What do we obtain? 0 and 1 and 0, 0 and 1 and 1, also 0. Because if even a single transistor is on, whether A is high or B is high, meaning the gate of the MOSFET is above the threshold voltage, either one of them is on, it connects the output to ground. So output goes directly to ground, whether it's A or whether it's B or whether it's both A and B. So the output of two transistors in parallel is a NOR output. So by default, we obtain Z bar. If we are talking about an OR gate, we obtain Z bar. So if we wish to have an OR gate, we connect a separate inverter at the output of those two transistors. So we need at least 3 transistors to have a OR gate. Okay, so by default, we obtain a NOR. And on the next page, we'll see by default, we can obtain a NAND gate. So again, these are some straightforward switches. Either one of them is on, the output will connect to ground. Okay, so we get a NOR gate. 2 transistors in parallel, we get a 2-input gate. 3 transistors in parallel, we get a 3-input gate. 10 transistors in parallel, we get a 10-input gate. So add more transistors, you get multi-input gates. And that's how we can obtain multi-input gates. Oh. Makes sense thus far? Okay. All right. Logic AND and logic NAND. Here Z is A and B. A logical AND is similar to mathematical multiplication. Not exactly the same, but very similar. So akin to mathematical multiplication. Operation is the same, except the connection is now in series. So you have two transistors connected in series, cascaded one after the other. So the source of the first one is connected to the drain of the second. The source of the second is connected to the drain of the third, and so on and so forth. And again, the operation gives us a NAND gate output because a NAND gate if you apply A and B and you have output Z, what do you obtain for a NAND gate? This is going to give us 1, 1, 1, 0. In order for the output to be low, both inputs must be high. So if we apply A, actually let's look at the other way around. If A is 0 or B is 0, output is cut off, it's high. In order for the output to go low, both A and B must be plus 5 volts to turn on both MOSFETs so that the output is connected to ground. Okay, for any other combination, output is always going to be plus 5 volts. So it's like a series. If you want multi-input gates, you simply add more transistors. So let's say you wanted a 10 input AND or NAND gate. We connected 10 transistors in series. If you have holiday lights, they're connected in series. If any one of them blows out, all of them are off. And so that's kind of the same logic here. 10 transistors in series. If even a single input is 0, then the transistor is off, output is high. So for all combinations, output is always going to be high, except when all inputs are high, then the output is connected to ground and it goes to 0. And hence, we obtain a NAND gate by default. To obtain a AND gate, we connect a single separate inverter circuit. That's it. That's how we can create logical AND, NAND, and OR. Okay. Did all of that make sense? All right. And again, you have these in your lab kits. If you wish to experiment, you can go ahead and do so. Right. All right. So we'll end class here today. This is where we stop at the earlier section. And so we'll end class here today, and I will see you all on Tuesday. And I will post reminders again. Quiz is not on Tuesday, it's on Wednesday, just to give a bit more breathing room over the weekend. Unless students overwhelmingly like say, I want the quiz on Tuesday. All right, I'll bid everyone a good weekend. Get caught up with your schoolwork, but also take some time to relax, chill out, and enjoy a little bit. All right.